as well. Okay, great. Well, our pleasure to have Bruno again, and we'll give the second talk on non-abelian Hodge theory.
All right, thanks. So I continue what I said yesterday. So yesterday I stated and I tried to explain the main theorem, which was this result due to Corlett and Donaldson. And Simpson. So I'll remind you what are the objects. The objects is we start with X omega compact Keller manifold. And then we want to understand a local system, predictive local system in them. And so we were considering on the one hand category of semi-simple representations of phi1 of X. So finite dimensional complex representations. And the final statement was that this thing was equivalent to the category of mu omega polystable Higgs bundles on X with vanishing Chern classes. Let's say E theta with vanishing Chern classes. Right, so I explained that this was an enhancement of this result of Narasimhan and Seshadri for compact representations in compact groups. And that the proof was essentially, the main object was a metric object. So you use the Keller metric to enhance this to a statement about metric objects. And so the intermediate guy was the category of pluriharmonic bundles. On X. So this was the picture. So let me recall what a pluriharmonic bundle was. So it was C-infinity bundle E with a flat connection D. And a Hermitian metric H on E. And the condition was the following. You start with your flat connection, and then you decompose it using the metric into a Hermitian connection for H. So plus a self-adjoint form. So alpha H is equal to alpha H dual with respect to the metric. And then you can decompose it now according to types. So this is a C-infinity connection. So I decompose nabla H as being del H plus del bar H into 1, 0 part and 0, 1 part. And alpha H exactly the same way into 1, 0 part, which is theta H. And because this guy is self-dual, the 0, 1 part is theta H star. Okay? And the requirement for this guy to be a pluriharmonic was that if you form the operator d double prime, which is del bar H, and here this is where the interesting things happen, is that you are mixing the 0, 1 part with the 1, 0 part of the form, and the claim is that you want this guy square to be 0. And so this is equivalent to asking, if you look at it, so I'm just repeating what I did yesterday, that this operator defines a new holomorphic structure on E, not the one coming from the flat connection, except if theta is 0, which is the entire case. And this has to be equal to del bar H of theta H. So this guy has to be a holomorphic one form, with value in the endomorphism for this holomorphic structure. And some integrability condition, the 0,2 part of this thing. So this is the 2, 0 part, this is the 0,2 part, this is the 1, 1 part. and the two zero part is theta, which theta is equal to 0. At the end of the day, these are the constraints on your metric to be called pluriharmonic. And so you see that if you have such a bundle here, then what you can do is you map it to just underlying flat bundle. And if you are here, you just map it to the associated Higgs bundle. And the Higgs bundle is, you put this holomorphic structure on this infinity bundle, and the Higgs field theta, well, this is this theta H. Okay.
Could you remember what polystable?
Yeah, so I defined yesterday, so mu omega is the slope with respect to omega. So you take the first Chern class wedge omega to the power n-2 divided by the rank. And polystable means direct sum of stable of the same slope. And stable, you define it in the usual way, asking that for any coherent Higgs subsheaves, the slope is strictly smaller than the slope of the ambient E. Okay.
Can one understand what happens if one changes the Keller metric, keeping its geometric?
Yeah, so it's pretty complicated actually. I thought after that because I discussed with Bhargav yesterday and he asked me basically the same question. So in the unitary case, you had exactly the same statement. You replace Higgs bundle just by holomorphic bundle. And the remark is that in that case, the situation is much easier because the functor for semi-simple representations to polystable bundles is canonical. You just take the associated flat bundle and the underlying holomorphic bundle. So the morphism, the functor is independent of the choice of the Keller metric on the base. Now, so this category depends on the Keller class of omega, and there is no way you can get rid of this. It's really dependent on this. But now the problem is that the actual functor depends not on the Keller class, but on the actual metric. So if you change the metric in the same Keller class, you associate another bundle, which will still be in the category of the same polystable bundle for this given Keller class. So the situation is pretty tricky. This is the best I can say about this. It's pretty tricky. So it's not true in the general system that if you fix different Keller classes, you get the same polystable bundles. This is true only for usual bundles, but not for Higgs bundles.
You see that unitary is easier, but variation of a structure, one has also the same image.
So for variations of a structure, there are some kind of the most algebraic case where the construction, in some sense, the pluriharmonic metric is just a Hodge metric, the one coming from the polarization, changing the signs alternatively. And then this guy is just graded, so it's completely functorial. It's much better. So for those ones, it's much better.
If you change the metric in the class, the Keller class, and you get an automorphism.
So you get the same category of objects, but the functor is not the same. You do not realize the same object.
Right. So then the automorphism you get in that category.
Yeah, so exactly. So what would happen is that I started, but I didn't have time to really think more deeply. So you write the difference of your two metrics, you write it as del bar of some function. And so this means that those functions naturally act here, but I stopped at that point. I didn't have time to check if you can say something more or not.
So you don't know if it's like holomorphic or something, or it's probably not. Okay.
Would it be easier to understand infinitesimal change of the metric?
This, I think, should be easier to do, but again, I didn't do it. All right, so this is what I explained yesterday, and yes, today I want to be, in 2 lectures I cannot explain everything, so I decided to try to give a general principle about harmonic stuff and why you get naturally this kind of objects. And then all the interesting things concerning moduli spaces, I mean, I would have to skip it just because not enough time. So, so I want to talk a little bit about the proof, but what is the general principle? So the general principle, I think it's pretty nice because this principle is also the one that underlies, for instance, recent results about K stability and special metrics, this kind of stuff. So this is exactly the same principle. So, and this is always the general, so the general principle has a name, and the name is Lagrange. So by that, I mean the following, that what you try to do, you enrich some mathematical objects using a metric, and and the way you enrich it, or you lift it, is by minimizing a one-chosen function. So it's very vague, but this is a general principle. I did not manage to formulate it in a better way. So let me try to illustrate what I mean by this. So the simplest example, I go back to what I started with yesterday, is classical Hodge theory. So in classical Hodge theory, what you do, well, as I said, basically you try to enrich cohomology classes by representing them by better representatives, depending on the metric. So if you have a compact manifold, and then of course, the natural invariant is its cohomology, as we said yesterday, the Petit cohomology. But if now, let's suppose we fix a Riemannian metric. On M, and then what I can try to do, we can try to start with closed forms on M and look at the natural projection to the cohomology and try to find a natural section defined by the metric. This is exactly what we are doing. Or even more generally, you can take all forms and try to find a natural functional such that when you minimize it, you find closed forms which have even better properties. Okay? So this is exactly what we do. So you basically what you do, you look at the following functional. You take all the forms, infinity forms of a given degree, and then you get the following functional. So if I take a form alpha, first thing I would like to do, I want it to be closed. So I would like d alpha to be 0. So I look at every point, and what I can do, I can use the metric. So this will be the G defined by the G metric. So of course, the metric on the Riemannian manifold induces a metric on the sheaves on the bundles of all possible forms. I can take this at each point. This is well defined. Okay. And now what I can also do, I can also take the adjoint operator for this metric, as we saw yesterday, and do the same thing. And I can do that at every point, and then integrate on M. This is easy because M is compact with respect to the volume G.
So what is alpha sub z? Very basic.
Sorry?
What is alpha sub z?
No, it's alpha sub x. So I'm just saying that I take the norm. So this is one form. So this is a section of the cotangent bundle, and at the point x, I take its norm at the point x. So this is an L2 norm that I'm defining this way, and this is usually called the energy of the class. So this is the G energy of alpha, and D star G is the adjoint, the G adjoint of D. Okay, so now what you want to do, you want to minimize G. So you have a functional on this infinite dimensional space, and minimizing, it means you apply the general Euler-Lagrange calculus. And so if you look at what Euler-Lagrange tells you, so in other words, I'm looking at the critical points of this functional. I take the differential. Of course, I'm working on some infinite dimensional manifold, so I have to be a bit careful. But what you get at the end of the day is exactly this equation. Well, if you derive, you see exactly what you do. For a tangent vector there, you would take the scalar product of d alpha at the point with the tangent vector and so on. And so it's very easy to write. And what you get at the end of the day is that the Laplacian for G of alpha has to be 0. Well, this guy is nothing else than d star G plus star G D. So I'll let you make the exercise to refresh your memories about differential calculus. But this is what you get. So this is super classical. And you see that you get exactly what you want. You get the forms such that their D is equal to 0, but also their D star is equal to 0. So the D is equal to 0 is the condition you want, they are closed. But the D star condition chooses a better representative among all the closed forms. This one, okay? So this is what classical Hodge theory is doing. Now you can generalize this idea to harmonic maps. And now what I do is, rather than having only one compact manifold, I take two. And I put some Riemannian metric on them. And now what I want to do, I want to try to realize homotopy types of maps between M and N. Okay? So I look at map from M to N, and I want to define a function. So let me define the function, which will depend on the choice of the two metrics. But if I take a map from F to N, what I can do, I can take its differential at a point x of M. So what is this differential? This differential df is actually a global section of over M of T star M tensor F pullback Tn. Okay, so because M has a Riemannian metric, this guy has a metric, this vector bundle has a metric, and this pullback also has a metric coming from the metric on Tn. And so this means that at each point, this thing has a norm. And so this means that I can take the norm induced by the metric of M and N there and do exactly the same procedure. Try to minimize this. And again, I can write the Euler-Lagrange equation, this. And if I look at the Euler-Lagrange equation, you get the following equation, that the Laplacian of f has to be 0. And what is the Laplacian? Well, you take exactly this differential, seen as a section here. And then on this, you have a natural connection induced by the Leavitt-Civita connection here and the pullback of the Leavitt-Civita connection there. So what you do is you take this connection, but actually it is a star, the joint for the induced metric coming from here and here. Okay. So this is a degree 0 operator. So this thing is really, so these things belong, and the equation is that this has to be 0, but this is belongs just to, this is just a global section of F star Tn. And the equation that you get is that one. Okay. And all right, and the hope is that you will find in any homotopy class, if you are lucky, maybe you are able to realize a better representative. Okay. The problem is that there are obviously some topological constraints. It's kind of naive because homotopy types are super rich, right? I mean, so there are a lot of abstractions. So such harmonic maps do not always exist. So let me give a simple example. So the example is, let's try to just look at the simple, very simple homotopy types. Look at, take a surface of genus G, and let's try to understand the maps to S2, sigma 0. Okay, and here everything is super simple because this is a k pi 1, and so this thing is entirely classified. The homotopy types from sigma G to S2 is entirely classified by the degree of the map. There is nothing else. So this is N corresponding to the degree of a map. Good. Now there is a nice, not completely easy theorem due to Higgs and Wood that tells you that if the genus is smaller than the degree of the map, the degree G of the map, the degree that you choose here is at least the genus, then if you have a map from sigma G to S2, which is harmonic, so of course here when I say harmonic, I'm putting the constant curvature metric on S2 and the natural -1 curvature metric on sigma G if G is of genus larger than 2, and the flat metric if G is equal to 0. So So this map is harmonic for the canonical metric if and only if actually it is holomorphic. And so this means in particular that if you look at the two torus, so sigma 0 and to S2 of degree 1, so it's a very stupid map. Two torus is given by a square where you identify this with this and this with this. And to map it to the sphere, you do the most obvious thing. You just contract all the boundary to a point. So you are just covering the sphere by your square, right? And the claim is that there is no harmonic representative for that map because otherwise this guy would have to be holomorphic. Okay. So does not exist. Harmonic representative. Okay.
Sorry, why is the degree n instead of z?
Sorry?
Why is the degree n instead of z?
Why is the degree?
And then why are the homotopy type on the right-hand side of your top expression? Why is that n?
Well, because you can choose any degree. I mean, any degree is reasonable.
A degree
I'm saying you can have negative degrees.
Yeah, okay. I'm working with everything oriented.
Okay, I see.
Sure. I could have negative degrees otherwise, but let's restrict myself to homotopy plus preserving an orientation. Okay, so this means that you have to be a bit more reasonable in your expectations. So a wonderful theorem due to Els and Simpson is the following. That actually there are no obstruction if the target has a non-positive curvature, in particular if it is a k pi 1. So when it implies it is a k pi 1, in some sense it explains why there are very little topological obstructions. So if you have MGM as above and MGN, and now compact Riemannian, so here I insist on compact. And suppose that the sectional curvature of Gn is non-positive, then any homotopy type map from n to n can be lifted amidst harmonic representative. Which is essentially unique. It's not unique, it's unique up to geodesic translation in n. Essentially. So, so that we understand a little bit better what we're doing, I will not give the proof, but let me give the idea.
Holomorphic maps, give examples of this.
So here, everything is Riemannian. So it's purely Riemannian.
If you have Riemannian surfaces, though, with negative.
So if you are between curves, dimension 1, then yes. So holomorphic implies harmonic. Okay, so let me try to give an idea of the proof. Well, it's a heat flow method. So, and this is a general principle in this Lagrange business. You start from a random solution, and then on the space of all maps, you try to follow a gradient flow. So you start at F0, some smooth map from M to N. And then, so of course, in the background, there is the fact that in any homotopy type is realizable by a smooth map. It's classical, but you do it. And then you try to solve the following. The claim is that what we want to solve the following heat equation. That I want to construct a one-parameter family of morphism from M to N, such that I have the following equation. Right. where this is what we want to realize. Why do I DFT? So why do I want to do that? Because if I do that and I try to compute the variation of the energy of the map FT, then by definition this is d over dt of the scalar product DFT with itself. And then this is integral over m. I change the integration with the differential. And so I get 2 integral of m d over dt of t, dft, with dft. I should have put on a sign. So always this problem with the gradient that you never know which side you put on it. But okay. And so now what is d over dt of dft? Then by definition, this is nabla df over dt. And so this is actually nabla, if I follow my equation, this is minus nabla star dft, ft. Actually. And so you see that when you replace in this expression, you see that then d over dt e of ft. So this is a standard method. So it will be zero. And so it will be negative. So the energy will decrease. So right, the picture is you have this infinite dimensional manifold of map on infinity from m to n. Start at the point f0, and then you have this gradient flow here. So which is given by this vector field at each point. So you have a gradient flow. And you try to follow it. And you see that along this gradient line, the energy decreases, and you hope to be able to conclude from that there is a limit. And this is where everything becomes PDEs, and depending how much you like PDEs, I don't like them, I'm not good at that, but at least you understand the general principle. And the general principle here, so PDE theory. So by this I mean that you need a short-time existence theorem. So you want to be able to solve this equation in the short time. Well, this is a general parabolic equation, so short-time existence is not a problem. And now you want the long-time existence, so that you don't want the energy to blow up. And this is what is ensured when you make the computation by the fact that the sectional curvature of the target is non-positive. So ensures no blow up. And using this, you prove that there exists a limit, which is a stationary point of this business. And so it will exactly minimize the energy and satisfy the equation. And there exists f infinity limit, which is harmonic. Because at the limit, the energy cannot decrease anymore, which means exactly that this nabla star is zero. Okay, so that's the general idea.
Will you really have limit, or do you need to take a subsequence?
So in general, you take a subsequence, but in this particular case, I think whatever subsequence, you get the same one.
Can you tell the picture of what goes wrong in this example you were giving?
Well, exactly this. There is actually no long-time equation, no long-time solution. All right. So why is that related to what we want to do? This is related directly to this side, the passage from your semi-simple representation to the Fourier harmonic metric, and so this is the work of Corlett Donaldson. So how do you do this? How do you see that?
Sorry, Bruno.
Yeah.
Are you saying that if there is long-time existence, then you always have a limit, or that's yet one more?
No, I mean, it's not automatic. It's HPDs. Once you have long-time existence, you still have to prove that you can find a subsequence, a sequence such that when you extract, there is a limit.
And you use the curvature being negative for
That's what I thought.
okay.
All right. So what is the next step? Well, basically, the next step is to try to find in Simpson theorem in a situation where there is no complexity. So yeah, I want to have this theorem, and below I will write some equivalent version of that theorem, and this is the theorem of Donaldson and Corlett. So it tells you the following. So basically what I want you to think about is the typical case here in this compact setting, here in the compact setting, is a case where Gn is a locally symmetric space of non-compact type. So something like SLN modulo SON modulo a co-compact lattice. Then it will satisfy those properties. Or SLNC modulo UN modulo a co-compact lattice, but now I don't want the lattice to be co-compact. That's exactly the point, or discrete, or whatever. So this means that I fix a reductive group G, and you can think this is GLN of non-compact type. So over R. So, and then what I can do, I can look at any representation rho from pi1 of M to G. Okay. And now the claim, and there is now one condition, which has to be thought as a stability condition, is that if rho is reductive, this is actually equivalent to the fact that there exists a map from the universal cover to G mod K. So G mod K is a symmetric space associated to G. So if G is SLN R, K is SON, maximal, it's always maximal compact. The case I will be interested in is GLNC modulo UN. There exists an F which is harmonic of the natural metric. So again, MGM is fixed now and compact. Riemannian. So compact is important, but I keep the compactness only on the source. Harmonic and rho equivalent. So to make the link with the previous theorem, just imagine that rho is discrete and with an image co-compact lattice. And in that case, this means that this map actually descend because it's rho equivalent. It would go to G mod K mod the image of rho, so lattice. And then when you are in this situation, if the lattice is compact, you can apply this L-Simpson theorem because this guy has non-positive curvature. But I want to get rid of this discreteness assumption. So you replace by some equivalent statement at the level of the universal cover. Okay. And so what is the meaning now? Because I defined harmonic by minimizing an energy, but now I'm something non-compact. But actually the energy functional, it's equivariant, so it's defined downstairs. Okay. So so this harmonic here is really minimize the energy over M itself of the same functional. And so this is exactly the same equation. And by Lagrange, this is again nabla star T F is equal to 0. Okay. Makes sense? And you see that the compactness on the target has been replaced by this stability condition on the representation, that it has to be reductive. By reductive, I mean that the Zariski closure of the image is a reductive. Okay, so let me now make the link with the theorem there. if G is equal to G and C, which is a case of interest for me today, then you see that G mod K, what is G mod K? This is G and C modulo U, and this is exactly the space of metrics, of space of Hermitian metrics on C to the n. Because I fix the standard metric. G and C acts naturally on that metric. And of course, it acts transitively on the space of all possible metrics because I can always choose an element mapping a base to an orthogonal basis for a given new Hermitian metric. And the stabilizer of the standard one is this UN group. Okay, so that's this. So now let's try to understand what is a map which is rho equivariant in this situation. Well, this is the same thing as a section of the bundle of metric for this representation, which means that this is the same thing as a Hermitian metric on the bundle, which was the one that I defined as being rho, namely on m tilde times c to the n I1 of m rho. Right, which is exactly the kind of thing I'm looking at here. I'm looking at, so H is corresponds exactly to such a map. So now I have to understand what is the meaning of pluriharmonic metric in this sense, and the theory of harmonic maps to that space. And the answer is, so actually now if you recollect what we started with, so if we had ED and we have a metric H, then we decomposed D as being nabla H plus alpha H, it's still on the board somewhere here. Actually, you see that alpha H is exactly TF for the corresponding harmonic map. Okay, so what I define as being the energy is really the norm of this alpha H. So E of H.
Is the proof of the theorem of Donaldson-Carlot, the same? You do the flow.
So I will come back in 1 second what you have to add. So you see this, and so you see that now you can interpret what it means for the metric to be, for the map to be harmonic in terms of the metric. So F is harmonic, so FH, corresponding map to that metric, FH is harmonic in the sense I defined. Well, exactly when Laplacian of the differential, but the differential is alpha H. So exactly when nabla H star, alpha H, is equal to 0. And you see that this does not seem to be the same thing as those equations. Okay. So now, nevertheless, so this is what I would call a harmonic metric, and this is what I would call the pluriharmonic metric. And now one miracle occurs in this theory is that actually one is equal to the other, although this equation seems much weaker. So it's easy to see that this equation, these conditions imply that condition. But in some sense, this thing is just a trace of two form, and you are controlling the two form using its trace as a 0 form.
Actually, can I ask a question related to what you started with?
Yes.
Which is, how does the notion of a pluriharmonic bundle depend on the Kähler metric? I mean, obviously a harmonic bundle does.
Yes.
But isn't the notion of a pluriharmonic bundle independent of the Kähler metric?
It becomes independent of the Kähler metric for the reason that it's essentially the same thing as being harmonic on each curve.
Yeah, right. And there's a component there. But then doesn't that mean that the Kähler metric?
No, because it will not be the same metric depending on the one that you choose that will realize your thing.
I mean, I just don't see the Kähler metric showing up in these equations.
Maybe we discuss this later.
Yeah, sure.
So what is the proposition? The proposition is that if you work in the Kähler setting, so this means if I remind you that d square is equal to d prime square is equal to 0, this was a condition. And then I claim that this is equivalent to saying that H is actually harmonic. And those conditions are what? Conditions are d square is equal to 0, but now it's only nabla H star alpha H is equal to 0. And if you think about it, what is this? Well, in this business, you have the Kähler operator lambda on forms. And the conditions is the same thing as saying that lambda d square equal to 0. So you have this this square is a two form with value in the endomorphism. And when I apply this lambda, I get only a zero form, so a global section of the endomorphism. And the claim is that this zero form is actually enough to control the full operator. Okay. So what time is it? I wanted to give the proof, but I'm so late that maybe I don't want to give this. So the proof is not very difficult. Actually, the proposition is due to originally to Simpson, and Hughes have a much more general statement about when a harmonic map between two Kähler manifolds is automatically pluriharmonic. So this is their true theorem. I think in this case, I found in the Bourbaki seminar by Le Potier that the proof that he gives is the lemma that you give him. It's very nice. I wanted to give this, but I think I will skip it just because of time constraints. So now let's go back to this theorem and let's try to give an indication how you prove this. So there are two things to be proven. The first thing to be proven is suppose there is a harmonic map, then you want to deduce that the representation is automatically reductive. This is the easy part. And the difficult part, of course, is the converse. You start just from your reductive representation and you want to construct this harmonic metric. And okay, so let me try to give some indications about that. So, sorry, to answer your question, this duality uses the Kähler metric because this is at the level of forms. Wow. So the full duality, you use the Kähler metric on the base. This is the trick. You are not at the level of functions. So how to prove Donaldson Correlate? So in one direction, you want to prove existence of harmonic map, of harmonic metric, so such a map implies that rho is reductive. So this is not difficult. This is a nice exercise in connections. So what is the proof? So you start with your flat connection. So you have your representation. I incarnate it in a flat connection on my bundle D, and I choose any metric and I decompose it again like this. So this guy is self-adjoint, and this one is a Hermitian connection for the metric. And now suppose that the metric is harmonic in the sense I had before. And so what do you have to do? You have to prove that, suppose that you have a subbundle inside E, which is D invariant. So you have a sublocal system, you want to prove it is a direct factor. Okay. So at least as a C-infinity decomposition, you can write it as E1 plus E1 orthogonal for the metric H, as C-infinity bundle. Now, what is the shape of your connection in this decomposition? Well, first you have the restriction to the subbundle, so it's flat, so here you get 0. Of course, you have the piece which is going from this orthogonal to itself, but then there is an additional thing here, which is eta. I call it eta. And what I want to prove is that actually this eta is 0. This is what I have to prove. Okay, so now what I do, I follow this decomposition. And if you follow this decomposition, so what will be the Hermitian connection associated to this? Well, this will be the Hermitian connection associated to this, the Hermitian connection associated to, so H1 is the restriction of H to E1, and I call it E2. Let's call this can be E2, it's easier. And then, actually what you get here, you get eta over 2 and minus the star over 2. Let me not write star with respect to H, but okay, so this is the Hermitian connection that you get. And as a one form, what you get, if you make the computation, you get alpha 1, alpha 2, which would be the corresponding decomposition of D1 and D2. And then you get eta over 2 and plus eta star over 2. Okay, so at least the sum should be that one. This is what you get. So this is my nabla H, and this is alpha H. So now what I do is this connection is on E. Let's look at the induced connection on the endomorphism. So look at D acting on endomorphism of E. And now endomorphism of E, of course, I can write it as blocks. And there I can apply nabla H, the Hermitian connection, to, there is a nice section on the endomorphism. As soon as these guys split, what I can do, I just take the most naive section, non-trivial section, which is minus identity on E1 plus identity on E2. Just changing the sign on one block to see what happens. If you do that, you get the following. You get that nabla H of this section. Well, this is first nabla H1, nabla H2. I just applied my formula, I computed nabla H there, of minus identity, plus the 0 matrix 0 eta over 2, minus eta star over 2, 0, and then I get the bracket. I'm using the usual form of a connection acting on endomorphism. This is just your connection applying there, plus the bracket of the one form with your endomorphism. And so if you make the computation, you see that you just get 0 eta star 0. So you get this. And so now let's try to understand the metric, the scalar product of alpha with nabla H alpha, of nabla HS, sorry. So the L2 metric of this thing, alpha H. And then what you get, well, you get the integral over M by definition of the scalar product of alpha with nabla H S at the point X, the volume. Next. And so this is just a trace. So I'm sorry, there are a lot, there are elementary computations. So this scalar product is just the trace of the product of the corresponding matrices. And so now you get that this is just actually just eta 2. But this thing, on the other hand, this is of course by adjunction. This is also nabla H star alpha applied to S. So now you see that your condition that the metric is harmonic is exactly that this guy is 0. So we get that this scalar product has to be 0. This is the L2 norm of eta, so eta has to be 0. So we have proven this reductivity. So just to give, there is no miracle in some sense in this differential geometry stuff, at least for this kind of implication. So now, as I said, the difficult part is going in the other direction. Suppose I start with row reductive, then I want to exhibit the metric. And here things become, so the general procedure is exactly the same as in Hill-Simpson. The local existence theorem is still because this is a heat flow. The problem is to prove exactly what we said, that we can find a sequence converging along this gradient line. And this is ensured by the reductivity. The reductivity ensures you that the mass, the whole energy is not escaping to infinity. You see, if you had a representation that fixed a point at infinity and you try to construct by approximation along this gradient flow a sequence of harmonic maps, well, you will find some maps, and then actually the map will escape to infinity where there's a fixed point for the monodromy. So this is what is called escape of mass in this kind of business. And this is exactly what is prevented by this. Of course, you have to prove it works, but this is the hard part of the theorem. Okay, so now I want to continue. So basically, I try to explain this. So now let's try to explain this. So this is exactly the same strategy, except this is even more difficult. So if you think about this heat flow, this is a second order PD. And here, for the other side, we are not so lucky. We'll get order 4. Questions about? But you see, this is always a general principle, and after that, of course, there is a lot of techniques in partial differential equations. All right, so so now we're on the right side of the board, and so again, there are 2 directions. We want to prove that if we have a pluriharmonic bundle, so what do we have to prove? We have to prove that if we start with a pluriharmonic bundle, well, we know that we get a Higgs bundle, so what we have to prove? The fact that it has vanishing Chern classes is obvious because it comes from a guy who has a flat connection, so the Chern classes of script E are the same as the real Chern classes of E, which are 0 because just a standard computation of the Chern classes using the curvature. Okay, Chern veil theorem. Sorry, I was not finding the word Chern.
It's real, not integral.
Sorry, it's only, I should have, I was more careful. The vanishing Chern classes, this is vanishing Q Chern class. All right, so you don't know what happens to the torsion. Because you are here, now I make a remark. I noticed that in all the papers written on this topic, nobody asked what are actually the topological bundles that you realize. Okay. And the answer is given in a paper by Pierre and Dennis Sullivan a long time ago. They prove that actually each time you have this kind of bundle on a finite étal cover, they become trivial. But as far as I know, in all these theories, this triviality is never used. This means that from the start, you could trivialize the bundle and write really only the one form as a connection and not care in some sense on the matrix form. Nobody used that. I don't know why. Yeah, I still don't understand the proof. I have to say, it's really a super nice paper. I want to study it in more detail, but I have never seen it used there. Okay, so the only thing that we have to prove for this to here, so this is fine, we have to prove the polystability. And basically, this is exactly the same kind of computations as what I described in the holomorphic setting, except so the really hard part is the other one. So the hard part, and this is the one I want to focus on. I start with this. I want to construct the metric. So ID, let's call it. It was 1, and let's call it 2 for 2. So you start with your pluriharmonic X bundle that you write as a C infinity bundle with del bar operator and Higgs, which is now in omega 1 for this del bar operator of endomorphism of E. Yeah. And theta is 0. So of course, things are much easier. I mean, are easier on curves because this condition is automatic. But okay, nevertheless, the general procedure is the same. So we want to construct a Fourier harmonic metric. H. So this means that we want the metric satisfy always the same thing. That if I write this as being nabla H plus theta H plus theta star H, maybe I remove the H now. We want. So now the game name of the game, because I start with the Higgs bundle, the second condition that d double prime square is 0 is automatically satisfied. These are the conditions for Higgs bundle. So now the condition becomes that d square should be 0. So we want that the curvature, usually denoted by F H, which by definition is dh square, is equal to 0. This is the equation that we have to solve. So what is a nabla H? Nabla H is a unique Chern connection on this. If I fix the metric H, now I have a holomorphic structure. So there is a unique Chern connection with respect to that metric, and this is the one. And of course, as we saw, this is something in A2 endomorphism of E. And well, the idea is the same. We minimize a functional. So now, what is a functional? Well, this is exactly. I looked at all the metrics, and on the space of all metrics, I want to associate the norm, the L2 norm of this. So the integral of a x of the square of the norm of that metric. This is a two form, so it makes sense. And of course, it depends on the Keller metric. Okay. So to play this game, things become a bit complicated. So we have to distinguish between the trace-free part and the trace part. So this means that I have, if R is the rank, I have the trace part identity of E plus what I would call F orthogonal. So this is the trace-free part. So actually, I should have written the proof for representation in SLN. This is a bit simpler, but okay. Then there are two decompositions. So this is with respect to the trace, and now there is decomposition with respect to the polarization on the Keller manifold. So in other words, there is a piece which is proportional to the Keller form. So we talk. This is a two form. So I want to decompose this two form as a piece with respect to the Keller form plus the primitive part. Let me erase the H. It's just too much. Right. Everything is depending on all these equations. There is H as a parameter, and we are trying to argue minimize depending on H. But let's forget this. So this is the primitive part. So putting those things together, you see that you can mix them. Namely, you can write F orthogonal, the trace-free part, as being the trace-free part of the primitive part plus omega over n, and then lambda of F. All right, so this was just some preliminaries about the notation. So now let's try really to minimize. So we write the Euler-Lagrange equation. So I'm minimizing. So notice that up to now, I'm not using any topological condition. I forget about the fact that I want the Chern classes to be 0. I start with any Higgs bundle. And actually, this is the general form of the theorem. So I want to minimize this at H is equivalent to say that this is what metric is called Young's. I.e., you want that the contraction, the trace of FH with respect to the Keller metric is a constant times identity. This is what is called a Young-Mills metric. So if you write it, you see that there are different ways of writing it. This means that F has to be equal to I times lambda omega identity plus the primitive part. In other words, you don't have a function in front of this omega, but just a constant. Or if you prefer, and this is maybe more manageable, is the one that I want to keep, is that actually lambda of this F perp is equal to 0. So this is very close to the conditions that we had on whatever. And lambda of a trace of F is a constant. So this one is not a problem. You can always renormalize by multiplying your metric by a well-chosen function. This you will get it without too much trouble. But now the important point to relate this problem with our problem is that actually by Chern theory, the Chern classes will in some sense control this norm. So the proposition is the following.
I'm confused with what happened for the redirect sum. Then it's independently, we have a metric on both, or is there a relation between the two?
If I take what do you mean? If I know that the bundle a priori decomposes at the direct sum and so on and so forth? Yeah, I'm not at that level. Yeah, I'm just working with the full thing and trying to analyze what I get. Okay, so there is so the proposition is that Chern class is constrain the possible value of this norm. In the following sense, actually only the first and the second Chern classes. So the first one is that if you look at this character, Chern character, so C2 minus C1 square over 2. So this is the number, you pair it with the class. This is the following thing. And this is really a characteristic class computation, classical with connections. Okay? Minus 1 over the rank, no, 1 over n, lambda of n is the dimension of X. So I hope I did not make mistakes in the normalization. So you get this first equation and you get the second equation. Is that C2 minus C1 square times R minus 1 over 2R. So R is the rank of the bundle times omega n minus 2. Then this is 1 over 8 pi square, the norm of the perp, minus 1 over n lambda of F perp norm square. So these are just computations. It's not difficult. It's just you have to use your exercise in differential geometry. But the corollary of this is that suppose that you have a Higgs bundle, Higgs with a Young-Mills metric. H. So this first part of this equation tells you that this guy is 0. So this means that this term is 0. If this term is 0, you get a constraint because this term is necessarily positive. So you get that necessarily C2 minus R minus 1 over 2R C1 square, omega n minus 2 has to be positive. So you get for free. Actually, it should be nice 2 as this is the corollary of 2. And 1 is that if moreover you know that the first Chern class is 0, and that the first Chern character C2 minus C1 square over 2, then actually you get exactly what you want, namely FH is equal to 0, i.e. TH is flat. So the moral of this story, so I'm already late, so yeah, I don't want to actually move faster. Right, those who want to leave, they can leave. I'm sorry, just want to finish this. maybe I would not give the proof of this, but so this is an immediate corollary because of what I noticed. This is not immediate, you have to work a bit, but it's true. And the corollary of this is that, so you get that E dH pluriharmonic is equivalent as saying that H is Young-Mills and Chern classes are 0. C2 minus C1 square over 2 n minus 2 is equal to 0. Okay? So the actual theorem proven by these people is that is the general existence of Young-Mills metric. So theorem that implies everything. So H in Simpson. So H in is the case of curved and Simpson in general is that if you have X omega compact scalar, and you take any X bundles without any constraints on the Chern classes, it admits Young-Mills metric if and only if it is E theta is mu omega polystable. So it's kind of a more clean statement. You get rid of the topological constraints, and it's just constraints in general. So I don't know if there are any kind of general applications outside of the topological case where the Chern classes are 0. I didn't look too much about that. As I said, this direction is similar to the proof that harmonic metric in polarized reductive in the flat case. It's very similar, it's the same kind of computation. And this direction is hard. So maybe I want to indicate briefly how it works. Nevertheless, so we look at the space of all metrics. So we have this function R, and where we look at the M2 square norm of the curvature. So of course, what you can do, what is the tangent space of this infinite dimensional manifold? Well, these are exactly the H-Hermitian endomorphism at the point H. These are just the H-Hermitian endomorphism of your bundle. And then you make the computation. And if you make the computation, what you find is that actually, if you compute the differential of FH at such a Hermitian endomorphism, we get the following thing. You get D double prime, which was our operator, given by the Higgs field plus del bar. Then you get D prime for the metric H applied on eta. And of course, those operators are interpreted on the endomorphisms, because this is an endomorphism. So this is what you get. And so the formula at the end of the day, going to cut short, is what is the differential of the norm? Right, so what is your Euler-Lagrange equation at such an H-Hermitian endomorphism? Well, you get that this is the real part of the scalar product for H of eta with 2i Laplacian prime for H, so for D prime of lambda FH. And so this means, if you think of it as previously as the gradient vector field, this means that the gradient vector field is, well, at a metric H, I associate a tangent vector at that point, which is this Laplacian H lambda FH. So this is a gradient vector field for the Young-Mills function. And so we want to proceed as before. We want to follow the gradient lines. And so along minus this one, Of course, I can change it and first of all divide by 2. That not cost much. And so what we want to follow, we want to solve the corresponding partial differential equation, which is h minus 1 dh over dt plus I Laplacian h lambda fh is equal to 0. This is what we want to solve. And this is pretty bad. This is order 2. This is order 2, so this is order 4. And then what Simpson does was already done by Donaldson in the unitary case. And this shows you that you are allowed to be super brutal with partial differential equations. So what you do, you just forget the Laplacian. So you study another equation. This one is too hard. So you replace by another one, which is by h minus 1 dh over dt plus I lambda fh is equal to 0, which is now order 2. And you hope for the best. You hope that although you are getting by this Laplacian, this is not anymore a gradient fit for this functional, but you're still hoping that this norm of the curvature will decrease along the gradient flow for this new guy. And this is what they do, and they prove existence, long-time existence of minimizing subsequence, and it works. So I'm super.
Why do you use polystable?
So exactly. So polystability is to show that if E theta, actually, I do it now factor by factor, I suppose stable. So if E theta is stable, then you show that there exists a sequence that converges. So it's crucial. I should have written this. This is crucial. So if E theta is stable, this is why it is used. You show that there exists a sequence of time going to plus infinity such that HTI converges to some h infinity, and lambda f h infinity is equal to 0. This is how you use the stability, but I don't want to enter into the details.
No, the thing I have trouble understanding, if things are bad for the limit, you need to construct some coherent bundle, and coherent bundle is a strange object from the.
Yeah, so there are a lot of things that I passed under the rug. It's not so bad. I mean, at least if you want to do it in the algebraic setting, you do the difficult case is the case of surfaces, but the kind of coherent things that you will get are not so bad. I mean, there were singularities only at points on the surface. And so, well, of course, yeah, it would be a full course for an expert in PDEs, which I'm not to explain really this. Okay, so I would just, sorry, I'm late.
All right. Any questions?
But my previous question, when on either side you have something which is a direct sum.
Yes, so you would get a direct sum of metrics.
Yes,
So what?
Yes, the metric is up to a factor, I think.
So the metric is up to a constant multiple, yes.
Yes, and so you have a number of.
You have a number of choices. This is perfectly correct. So it's unique on the big stratum where everything is stable, but of course, at the point where you're actually polystable, you have various possibilities.
Sorry, can I be annoying again? Sure. So on a curve, I think it doesn't depend because it's scale invariant.
I still think it depends even on the curve because let me think. You are still considering norms of one forms with even something.
No, all you can do is scale the metric on a curve. It's not on a curve.
Yeah, maybe you're right.
I think on curves, it's
On curves, that's fine.
And then on an algebraic thing, it shouldn't depend.
On an algebraic thing, it should depend. For Keller, I still
Yeah.
don't see any way of doing it.
Yeah, I don't know.
Anyway. Good remark.
Okay, let's thank Bruno again for next.